All right, I'm going to be working here on 12.8, which is change of variables, working problem number 15. And I put some stuff up here to remind you. First of all, what we're doing is we're doing the double integral over the region R of x minus 3y with respect to area. So we're back to double integrals right now. And the region that we're given is the triangle with these vertices. And we're also given that we're going to use this transformation to somehow convert this region into hopefully something that's nicer. Now, this region by itself could be done. I mean, this is possible to split this up right here and do it as a type 1 region and do two of them. So like here, we could do this as a type 1 and do that one as a type 1, add the two answers together. But the whole point of change of variables is to try and get a nicer region from an ugly region. So these are given to us, and that's a big deal that they're given to us. So the question is, what does this become in the transformation? So we're trying to convert that region in the xy plane to the uv plane, and hopefully it'll be a nice region. So let's start out by, let me move these a little bit. X equals 2u plus v, y equals u plus 2v. All right, give myself some room here. So let me first ask, what does this line become in this transformation over to here? So let's find the equation of that line. It has a y-intercept of 0, has a slope of 2 over 1. So this should have the equation y equals 2x. So what I'm going to do is I'm going to take that information, y equals 2x, and I'm going to rewrite this equation, replacing y with my substitution, replacing x with my substitution. So the left side is y, which is u plus 2v, must be equal to 2 times x. X is 2u plus v. And then I will multiply things out. U plus 2v equals 4u plus 2v. Notice I can subtract 2v from both sides. I get u equals 4u. Subtract u on both sides. 0 is 3u. Divide by 3, you get u is 0. So what I know is that this line, okay, gets taken over, and remember the line extends forever, but this line segment would be taken over to the line u is 0. So over here in the uv plane, if u is 0, then I imagine having a line over here, vertical line, u equals 0, that would extend forever like this. Okay, now what I'm going to do is I'm going to look at, let's take another line segment, which would be this one. Find the equation of that. So it has a y-intercept of 0, it has a slope of 1, 2, so it's a slope of 1/2. So that's just 1/2 x. Now I'm going to do the same thing. I'm going to ask myself, what happens to 1/2 x, or y equals 1/2 x? What does that line get taken to? So I'm going to write this down right here. Y equals 1/2 x, and y is u plus 2v. 1/2 x is 1/2 times x, which is 2u plus v. And that's u plus 2v equals, distribute the half through, u plus 1/2 v. Notice I can subtract u on both sides and they're gone. And then I can move all my v's to one side. So I'm going to add a half v to 2. That's going to give me 5/2 v must equal 0. And then just divide through by the constant, v must be 0. So this line gets taken over here to v is 0. V is my coordinate this way. So v being 0 is the line going like this. And then the last thing to do is to figure out what's happening here. So if I extend that up forever, we can tell the slope of this is down 1 over 1, right? Down 1 over 1. So the slope is -1. The y-intercept, we should hit up here at 3. So that should have the equation y equals -x plus 3. And I'm going to see if this marker is any darker. Write that down. Oh yeah, y equals negative x plus 3. So y is u plus 2v equals negative. Now x is 2u plus v, then plus 3. So u plus 2v equals negative 2u minus v plus 3. And here, neither one of the variables are going to cancel. So move all my variables to one side for right now. Add 2u, I get 3u. Add v, I get plus 3v equals the 3 that's over here. Divide everything by 3, you get u plus v is 1. And then what I'm going to do is I'm going to solve this for v. And so v is kind of like the y-axis is over there. So solving for v is like solving for y over here. So this is a line. It has not a y-intercept, we call it a v-intercept of 1. And it has a slope of negative 1, so down 1 over 1. And there. So you can see, I think it's obvious, that this region here, R, gets transformed into this new region over here, which we call S. And that S is a very clean type 1 region. What we have is that U here is between, actually it's not, yeah, it's type 1. U is between 0 and 1, and V is between a top function and a bottom function. Top function, remember this line right here, was V is negative U plus 1. So my V is stuck between negative U plus 1, that's the top, and the bottom was V is 0. So everything's looking good so far. What I need to do now is convert the integral over, the double integral. And so for this double integral, it's going to go from integrating over R to integrating over S. It'll be this function with this substitution in it. So it'll be x, which was 2u plus v, minus 3 times y, which was u plus 2v. And then I'm going to have with respect to area, but I have to put the Jacobian determinant in there. So I've got to figure out what this is, and I've got to place that right here. And then I can say, you know, du dv. So let's do our Jacobian determinant. I'm going to do that right here. So I need the partial of x with respect to u. So I look at here, partial of x with respect to u is the derivative of this with respect to u. I treat v like a constant. That's just going to give me 2. So this right here gives me 2 times partial of y with respect to v. So partial of this with respect to v is just 2 again, minus the partial of x with respect to v. Partial of this with respect to v is 1, times partial of y with respect to u, which again is 1. So you get 4 minus 1, which is 3. So I'm going to take all of this, I need another parentheses here, multiply it by the Jacobian determinant, which is 3, and then I can put du dv, or dv, oh, I have to do dv on the inside, du on the outside, because I have constant here and functions there. And then I'll erase this s, and I'll put 0, 1, and I'll put 0, negative u plus 1. Let me clean this up. Integral, double integral. Zero to 1, 0 to negative u plus 1. Let's see, I have 2 u's. I'm going to take away 3 u's, so I've got negative u. I've got v, and I'm going to take away 6v. I've got minus 5v, and then I have a 3. Oh, that 3 is going to multiply through. Or I can just pull the 3 out. That's fine. And then dv du. Okay, let's find the antiderivative. So I have, this is 3 integral 0 to 1. Antiderivative of this with respect to v is negative uv minus 5 halves v squared, evaluated from v equals 0 to v equals negative u plus 1 du. And now I just replace. I think I'll do something else also while I'm here. These are both negative, so I'm pulling negative out, make this a negative 3, make that positive, make this positive. So we've got negative 3, integral 0 to 1, and then let's replace v with this. So I get u times negative u plus 1 plus 5 halves v squared. Nothing gets replaced in there. And then minus, we replace, oh wait, hold on, v squared, that I'm replacing v, oops. This is negative u plus 1 squared, sorry. Now what we do is we plug in 0 for v, so that's gone, so I don't have anything there. Du. And this is equal to negative 3 integral 0 to 1 of, let's see, negative u squared plus u. It's just distributing here and here. This right here, if I square it, I get u squared minus 2u plus 1. That's what I get when I square this out. And then I multiply 5 halves through. So I'll save myself some time. If I multiply this through by 5 halves, get 5 halves u squared minus 5u plus 5 halves. And I'm going to integrate each one of those. So I'm going to get 5/6 u cubed minus 5 halves u squared, and then plus 5 halves u. Oh, shoot. You know what? I wasn't integrating yet. Oops. I'm just simplifying. Okay. I'll do integration on the next step. I'm getting ahead of myself here. Okay, that's just everything multiplied out, du. Now I will integrate. I believe I can combine some like terms together, though. Let me see. Maybe I should combine like terms first. Negative 3 integral 0 to 1. How about as far as halves, I mean u squared, so I can put those two together, and I should get 3 halves u squared. I can put the u's together here. That's going to be minus 4u. And then I have the 5 halves out there still. Du. Now integrate. Negative 3. Okay, antiderivative here is 3/6. So that's just going to be 1/2 u cubed minus 2u squared plus 5 halves u. Evaluating this, u equals 0, u equals 1. So when I plug in 0, everything's gone. But when I plug in 1, I should just get some fractions in here. So I get negative 3, let me see, 1/2 minus 2 plus 5 halves. And if I put 1/2 and 5 halves together, that's 6 halves, that's 3. 3 take away 2 is 1. So you should just get negative 3 times 1, which is negative 3. All right, there it is. All right, the next one I want to do, 17. So for 17, well, you know what? Let's do 16 first. I'm going to do 16. Double integral over r of 4x plus 8y dA. And we have a parallelogram that has the following points as vertices. Negative 1, 3. There. 1, negative 3. Here. 3, negative 1. Here. And 1, 5, which is up here. There we go. So I'm going to write down what these coordinates are. Negative 1, 3, 1, 5, 3, negative 1, and 1, negative 3. Oh, also, they give you the transformation. The transformation we're going to use is x is equal to 1/4 u plus v, and y is equal to 1/4 v minus 3u. Oh, wow, I have a meeting in 15 minutes. Okay, so I'm going to try and work quickly through this. All right, so let's figure out figure out what the lines are on these. This right here, this line is a y-intercept of 0, has a slope of down 6 over 2, so negative 3x. All right, and then this one right here, let's see. To find the slope, I can find the slope between these 2 points. So it's y2 minus y1 over x2 minus x1. So if I do this minus this, I get 2. And then this minus this, I get 2. So the slope of that's 1, so that's y equals x. And then I need the actual y-intercept of this. So the slope is 1, right? Up 1, over 1, up 1, over 1. Then if I go down 1, over 1, I should be here at negative 4, so minus 4. This line right here should have the same exact slope as this one because it's a parallelogram, but you can check it yourself, it does. Y equals x, but the y-intercept here is actually 4, so plus 4. And then this one right here should have the same slope as this one. You can check for yourself. Y equals negative 3x, but the y-intercept is actually, where are we? If we're here, 1, 5, then I'd go back 1, up 3, 1, 2, 3. So we would be actually at 0, 8. So this should be 8 there. Let me just double check that. Yeah. Okay, so now let's take a look at what these look like with these transformations. So if I let's take this one first, okay? Y equals negative 3x means that y, which is 1/4 v minus 3u, must equal negative 3 times x, which is 1/4 times u plus v. So we get, I'm going to multiply both sides by 4, and that'll get rid of those. So I get v minus 3u equals negative 3u minus 3v. My 3u's cancel, and then if I move things around, I'm going to get v is 0. So I know in my uv plane, one of the lines I have is v is 0, which is this. Okay, and now I take the next equation, which I'll do this one, y equals x minus 4, and rewrite that one. So y is 1/4 v minus 3u equals x, which is 1/4 u plus v, and then minus 4. I'll multiply both sides by 4, it'll go away, and then this will become 16. So v minus 3u equals u plus v minus 16, and then The v's will cancel. I can move the u over there. I get negative 4u equals negative 16, so u is 4. And if I graph that over here, remember this is the u v plane. U is 4. It's like this. And I keep this thing going. Now let me do this one. I rewrite this. Y equals negative 3x plus 8. So y, which is this, equals negative 3x. So negative 3/4. That's that, u plus v, then plus 8. So if I multiply everything by 4, I get v minus 3u equals negative 3, right? Because the 4 will cancel. Negative 3 times that, so negative 3u minus 3v. Multiply that times 4 plus 32. What cancels? 3u's cancel. And move this over, I get 4v equals 32, so v equals 8. So v is 8 is going to be, this is going to not be drawn to scale. Well, I'll just move it up. There's v is 8. And this one goes up there. And then finally, if I do this one, x plus 4. So I get y equals, here's x plus 4. Then multiply everything by 4. V minus 3u equals u plus v plus 16. Yeah, v's are gone. You get negative 4u equals 16. So u equals negative 4, which means u is negative 4 is over here. And you get this. So you can see that this region, this parallelogram, region R, gets transformed into this region over here, S, which is a rectangle, which will be very easy to integrate over. So now what I'll do is erase all this crap and roll over R. Okay, I'm going to set up my double integral over the region S, which is that. Now, I'm going to need to get my Jacobian determinant. So I'm going to have to calculate partial u with respect to x. Partial x with respect to u times partial y with respect to v minus partial, really doesn't matter what order you go in here with the multiplication, partial x with respect to v, partial y with respect to u. Okay, so I'm doing that now. Okay, so here's my stuff up here. Partial of x with respect to u, you can do that, you get 1/4. Partial y with respect to v, you get 1/4 again. Just distribute the 1/4 through, and then you'll have 1/4 u plus 1/4 v, and then here 1/4 v minus 3/4 u. Then the derivatives are really easy. Minus partial x with respect to v, which is 1/4. Then partial of y with respect to u, which is negative 3/4. So this is going to give you 1/16. Negative negative is plus. 3/16, which is 4/16, which is 1/4. So I know that I'm going to have a 1/4 I'm going to have to put in here. I have to rewrite this in terms of this. So what's 4 times x? Well, it's 4 times this. The 4's go away. You just get u plus v. What's 8 times y? Well, it's 8 times this, so 8 over 4 is 2. Distribute a 2 through. You should get 2v minus 6u. Now, that's this replaced. Now the Jacobian determinant, which is 1/4, I'll pull that completely out because it's a constant. I can do that. And then I need my 2 variables. And since it's a rectangle, it doesn't matter which way I go here. I'll do dv du. My restrictions on u are -4 to 4. My restrictions on v are going to be 0 to 8. I can clean this up and make that -5u plus 3v. And at that point, you should be ready to go. I won't do the rest, but you would get an answer here if you work this out of 192. Okay, I've got to get to a meeting, so gotta go. Okay, working on number 17, we're doing the double integral over the region R of x squared dA. R is the region enclosed by this ellipse, and there are my transformations. So let's take a look at this region first. This is the region bounded by this ellipse. So we have this ellipse here. So our region R right there. And this is the xy plane, so those are our two variables. And we're going to convert over to the uv plane. So we're going to transform this region into something that hopefully will be nicer. So let's go ahead and take a look real quick at what the transformation is. So what I'll do to figure out the transformation is I'll take this equation, I'm going to replace x with 2u, and then I'm going to replace y with 3v. I'm going to see what sort of equation I get from this. So if I square this, I get 4u squared, I multiply times 9, I get 36u squared. Here I get 9v squared when I square this times 4, so you get 36v squared equals 36, and that's u squared plus v squared is 1, which if I look at that in the uv plane is going to be the unit circle. And this region S, we'll call it, will be much easier to integrate over than this one, because I can use polar coordinates on that. But before I do that, I'm going to transform this integral. So this integral right here is going to be equal to double integral over S. Now x squared is 2u squared, so that's 4u squared. But then I need my Jacobian. So I've got to come in here. I've got to do some partial stuff here in order to finish this out, to get that to get whatever the Jacobian determinant gives me. Reminding you, since I know I did it in the previous problem, but you're looking at note, where's that darn thing? Where do I have it written out? It's note 12.8.3. So what we're going to need to do to get the Jacobian determinant is we're going to need to do the partial of x with respect to u times partial of y with respect to v minus partial x with respect to v times partial y with respect to u. So we need to figure out what that is. The partial of x with respect to u here is going to be 2. Partial of y with respect to v is going to be 3 minus partial of x with respect to v. There is no v here, so that's 0. And this doesn't matter, but this is also 0. So you get 6. So I'm coming back here. I have to say times 6, right? That's my Jacobian determinant. And then with respect to the new area. So that looks like it. I can clean that up a little bit. I can say that's 24 double integral over S of u squared dA. And now I look at this region and I say, all right, well, I'm going to go to polar here. So to go to polar, remember that our polar transformations were things like this. X equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. And that's all great when our variables that we're starting with are x and y. See, here we have u and v, so I can't use x and y, so I'm just going to replace my x with u, my y with v. All right, and those are my transformations. So from that, I know, of course, my theta to draw this region has to be between 0 and 2 pi. I know that my r has to be between 0 and 1. And then I rewrite this integral. So I have 24 integral 0 to 2 pi, integral 0 to 1 of u squared, but u is r cosine theta, so r squared cosine squared theta, times, now we have that we went to polar, so I always have to have the r, and then dr d theta. And so this becomes 24 integral 0 to 2 pi, integral 0 to 1 of r cubed cosine squared theta dr d theta. Just putting my r's together. And I also noticed that my thetas and my r's are split, so I can use that special property right now. And I can do two separate integrals and multiply the answer. So I'm going to say it's 24 integral 0 to 1 of r to the third dr times integral 0 to 2 pi of cosine squared. And I already know that when I do cosine squared, I'm going to convert it to 1 plus cosine 2 theta. And then there's a half there from the formula, and I just pull that out. So that's what I've got to do now. The antiderivative of this, so I have 24 times, the antiderivative of this is 1/4 r to the 4th, evaluated from 0 to 1. So I've got to figure out what that is, times antiderivative here, 1/2, antiderivative of 1 is theta, antiderivative of cosine 2 theta is plus 1/2 sine 2 theta, evaluating this from 0 to 2 pi. So I've got two evaluations to do, and then I'll just multiply that answer times 24. So I think I can fit this in right here. Get 24. Okay, when I plug in 1 here, I get 1/4. When I plug in 0, I get 0. So I'm just going to have 1/4 minus 0. And then the next one, when I plug in 2 pi, let's see what happens. 2 pi here, sine of 2 times 2 pi is 4 pi. Sine of 4 pi is 0, so that whole thing zeroes out. I get 2 pi times 1/2, so that's just pi. And then when I plug in 0, I get zeros here. So everything zeroes out, so minus 0. And so this is 24 times 1/4 times pi, which is 6 pi. Okay, working number 19, we're doing the double integral over the region R of x, y, dA, where we have the region bounded by the line y equals x, which is here, y equals 3x, which is here, and then the hyperbolas, we have x times y is 1. If we solve for y, we get 1 over x. This is the graph of 1 over x in the first quadrant. And then x times y equals 3. If we divide by x, we get y equals 3 over x, which is basically 1 over x just multiplied by 3. So it just stretches it out vertically. So this one will be above this one. So the region you can see bounded by the 4 curves is here. And that's a rather complicated looking region. So let's see if we can convert it into something nicer. Here's the transformation which they give us again. And so I'm going to try and do this transformation. I'm going to take each one of these and see what they turn into. So let's start with y equals 3x. Let's see where that goes. Y equals 3x. So y is actually v, and 3x will be 3 times u over v, like that. And then I multiply both sides. We get v squared equals 3u. Or you could say, how do we want to do this? We can have that u is a function of v or v is a function of u. I'm going to try and make v a function of u, so I'm going to do v equals plus or minus square root of 3u. I'll deal with that in a second, okay? Let's see what happens to y equals x. Y equals x turns into v equals u over v, and we're going to have the same story here. V squared equals u, so v equals plus or minus root u. Okay, let's see what happens to x, y equals 1. So x is u over v times y, which is v, that's a v, equals 1. The v's cancel, you get u is 1. That's very nice. And then finally, oh, I got my colors wrong. Oops, this was the blue one. Oops, I'll just redo it real quick. Y equals x, so u over v equals v. No, other way around. V equals u over v, same thing, but v squared equals u, v equals root u plus or minus. Okay, and then that one was nice, and then which one am I missing? The green one, which is xy times y equals 3. So x, which is u over v, times y, which is v, equals 3. So you get u is 3. All right, let's see if we can draw this in the UV plane. Let me erase this. I should remember that's the region R that I just erased. I'm going to try and see what the image of that is under this transformation. So we have, let's do the easy ones. U is 1. This is u and this is v. U is 3. So that means these are vertical lines. This. Well, you know what? I may as well use the colors. I have them, and I've got some time right now. So, okay. So the green one turns into this. The black curve turned into this. The blue curve. Okay, so we have plus root u minus root u. So we're going to have root u looks like this, right? And negative root u would be the bottom one, but I'll talk about that in a second. And then the red one would be plus or minus root 3u, which is the same as root 3 times root u. Root 3 is bigger than 1, so basically this is going to stretch this one out just to make it a little taller. So it looks like this. Let's just say. All right, so this is v equals root u, and this one's v equals that one was root u. This one up here was root 3u, sorry. Root 3u. And then I've got my two bounds on my u. So the question, I guess, becomes which do we take the positive or the negative, right? Because I took both the positives for this. Well, you can see that the reflection of this, right? If you reflect it down, which would basically give you the same region, just over down in the fourth quadrant. Why wouldn't something like that work? Let's check this out. Let's just take an example of a point. So if we did the negatives, I'd be down here. If I pick a point over here, let's see, I would have a positive u value and a negative v. So I'd have a positive u and a negative v, right? Positive u value, negative v value. And that would be a negative number, and that would mean x is a negative number. So if you go back to the original drawing we had, remember we were in the first quadrant,
And so it would be impossible to get a negative x number. So I can't use the bottom region because that would not correspond to the original region when I go backwards. So we eliminate this. I hope that made sense. So here's my region S. It's that region in there. Now I also need the Jacobian determinant, so I can erase this stuff. I don't need that anymore. By the way, that's a nice type 1 region for a double integral. I've got, if I draw vertical little line segment here like this, as I move that left and right, the red one's always on top, the blue one's always on the bottom. My u's are bounded between 1 and 3. It's pretty simple. But to get the Jacobian determinant, I need the partial x with respect to u, partial y with respect to v, minus partial x with respect to v times partial y with respect to u. So what is the partial of x with respect to u? Remember, x is 1 over v times u, so I'm treating 1 over v like a constant. This will be 1 over v. Partial of y with respect to v is 1, minus partial of x with respect to v. Well, now u is a constant. This is the same as v to the negative 1 times u. So the derivative of that is negative 1 over v squared times u. And then partial of y with respect to u is 0. So that's good, that kills that off. So we just get 1 over v. All right, a couple of more things to do here. I need to come back over to this double integral. I'm going to do the double integral over the region S. X times y, which is this times this, which is just u, times the Jacobian determinant, which is 1 over v, and then with respect to area. Okay. Now, let's go ahead and set up the limits of integration. So this becomes integral, let's see, u is going to be the one stuck between two constants, so 1 to 3, and then root u to root 3u, and I'm integrating u over v dv du. Good. Now let's go ahead and do this integration. We cannot split this up into two using that special thing because these are not stuck, both stuck between constants, so we can't do that. So I've got to integrate with respect to v first. So I've got integral 1 to 3. Now the antiderivative of u over v, remember u over v is u times 1 over v. So u is a constant here. Antiderivative 1 over v is natural log v. So I'm going to get u times natural log v evaluated from v equals root u to v equals root 3u, and then all of that du. Now that's equal to integral from 1 to 3 of, let's start plugging things in here. All right, if I do root 3u in here, I'm going to get u natural log of root 3u, and then minus, when I plug in root u, I get u natural log of root u, whatever that is, du. And check this out, I'm going to use properties of logs here. Remember, this is natural log of u to the half. The other one over here is natural log of 3u to the half. And so these powers can come out. So I'll do it right here. So I'm not doing any integration yet. This is u. Oh, the 1/2 came out. 1/2 u natural log 3u, and then minus 1/2 u natural log u du. And a couple other things I can do here. This right here is a product inside of a log, so I can split it into two logs. I'm, again, using more properties of logs here. So I'm going to do equals How about they both have a 1/2? So I'm going to pull 1/2 out, integral 1 to 3. So I have u, and then remember this splits into two different things, natural log 3 plus natural log u. And then minus the half already came out, u natural log u. That, I guess I can put parentheses out here like that. Du. Okay. And then I'll distribute that u through 1/2 integral 1 to 3. So I'm just going to distribute the u through here. I get u natural log 3 plus u natural log u, and then minus u natural log u. Ooh, that's nice. Du, and these cancel. Something tells me I should have seen that earlier. It's okay. Keep it going. Natural log of 3 is a constant. I'm going to bring it out. Natural log 3 over 2 integral 1 to 3 of u du. That's the only thing left, which is natural log 3 over 2 times 1/2 u to the second power, evaluated 1 to 3. And I think I'm getting close here. Plug in 3, we get 9. And then, so we'll get something like 9 natural log 3 on top, and then 2 and this 1/2 over 4 minus, when I plug in 1, I get 1/2. I get natural log 3 over 4, which is 8 natural log 3s over 4, which is just 2 natural log 3, which you could rewrite as natural log 9 because the 2 could go up as a power. So natural log of 9, or the book left it as 2 natural log 3. Okay, that's it for 19. Interesting problem. Okay, I'm looking at number 24. I've got a double integral over the region R of x plus y, the quantity x plus y times e to the x squared minus y squared. Here's the region. So they give you 4 lines. X minus y equals 0. You know, just solve for y here. You get y is x. So that's this one right here. Solve this one for y. You get y equals x minus 2. And then that's this one right here. You can do the same for these, and you get those 4 lines. You can clearly see the region of integration. Now, it's this problem, they don't give you what the transformation is. And you have to come up with it on your own. So there's a couple of ways you can look at this. You can look at the actual integrand itself and look for things that look obvious to you, like x plus y appears here. Notice x plus y appears here twice. That might be a good substitution. And then if you take the difference of squares here, remember x squared plus y squared, or minus y squared, is the same as x plus y times x minus y. So maybe x minus y would be a good candidate for a substitution or for a transformation. And notice x minus y appears here also. So there's something in the problem that should hopefully lead you to some sort of guess. I'm going to try this transformation. U is x plus y, and I'm going to try v is equal to x minus y. I'm going to see what happens. So I'm guessing here kind of. So let's see what happens to these things first. All right. So in this transformation, if I take this equation, all right, x minus y equals 0, what happens to it? Oh, you know what? I have a bigger problem here. I need to first. Well, you know what? Yeah, this will work out perfect. Watch. If x minus y is 0, if x minus y equals 0, then that implies that x minus y must be 0. That implies that v must be 0. If I take the red one over here, x minus y equals 2, that implies that, again, x minus y is v, that v must be 2. If I look at x plus y must be 0, well, that implies x plus y is u, so u must be 0. And if I look at the last one, x plus y must be 3, that implies that u must be 3. And that is a very nice region in the UV plane. So here's U, here's V. So what we have is that V must be 0. Okay, V must be zeros, basically like the V axis. V must be, sorry. Come on, Robert, get it together. V is 0. Excuse me. Is horizontal. V is 2. There. Why did I draw that in red, green? Things were going well. V is 2. This blue one here was V is 0. Green one, U is 0, which means this one. And then the last one, U is 3. And you can see it's a nice rectangle. I know my U's are between 0 and 3, and my V's are between 0 and 2. That's going to be a nice integral. So now we need our Jacobian. All right, so to get our Jacobian, we need to be a little careful here, because Jacobian is partial of x with respect to u times partial of y with respect to v minus partial of x with respect to v times partial of y with respect to u. But notice these are not solved for u and v. For x and y. I do not have yet x is some function I do not have that x is some function of u and v, and I do not have that y is some function of u and v. I don't have that yet. Excuse me, hold on for a second. Okay, I'm dying over here. All right. So let's try and get these to be functions, x be a function of u and v, and y to be a function of u and v. So here's what I'll do. I know that, let's solve this for x. X must be equal to u minus y. So x must be equal to, let's see. Oh, and let's solve this one for y, or for x also. How about that? X equals u plus y, right? So that's correct. Move v plus y, damn it. V plus y. So just move this over. So that's what those two are equal to. So you can say that u minus y must be equal to v plus y, like that, because they're equal to each other. And then move things around, you get u minus v equals 2y, right? Move this y over, v over, and then take 1/2 on both sides like this. And you have an equation for y in terms of u and v. So I've got this one. And then you could do the same thing to get what x is, but even easier, just take this right here. Take x is equal to u minus, now y, you know what y is, right? Y is this, so 1/2 u minus v, distribute, so minus 1/2 u and then plus 1/2 v. So just distribute through, and then put these two together, you get positive 1/2 u plus 1/2 v is what x is. So you have x as a function of u and v. So let me rewrite that up here. I have that x is equal to 1/2 u plus 1/2 v, and I have that y is equal to this. I'll distribute 1/2 u minus 1/2 v. Now I can come up with the Jacobian determinant. it's going to be partial of x with respect to u, which is this 1/2, times partial of y with respect to v. Partial of y with respect to v is going to be -1/2, minus partial of x with respect to v, which is 1/2, and partial of y with respect to u, which is 1/2. And so you get -1/4 minus 1/4 is -1/2, right? And remember in the Jacobian determinant, when you plug that in, you have to take the absolute value. So I think I'm ready to transform everything over, get this whole integral over. So we're going to be taking the absolute value of this at the end. Okay, it's the absolute value of that. Okay, so 1/2 is my Jacobian determinant. I'll leave those up there. Okay, here we go. Double integral over the region S. Okay, what was x plus y? X plus y was u. E to the x plus y is u, x minus y is v. So u times v. And then my Jacobian determinant, which was 1/2 with respect to area. And remember that the restrictions on u and v were both constants. So I'm going to go double integral. Doesn't matter which way I go. I'm going to go 0 to, I think it was 0, 3. Let me double check. I erased it. 0. Oh no, restriction on u was, well, I can do it either way, but I was going to do u first. Or the v on the inside, u on the outside. So like that. And then we have the 1/2. I should probably just pull that 1/2 out now. And then u, e to the u times v, dv, du. All right. And now that should be pretty nice to integrate. Just double check here. I've got everything rolling good. Yeah. All right. So let's take the antiderivative of this with respect to v first. And remember, u is a constant. So I have 1/2 integral 0 to 3. Antiderivative of this whole thing with respect to v should be e to the u times v. Check it for yourself. Integrating that from v equals 0 to v equals 2, and then du. So just double check. If you take derivative of this, it's itself times derivative of what's up here with respect to v, which is u. So a u pops out, which is this. Now plug in 2 for v. So 1/2 integral 0 to 3. Plug in 2 for v, you get e to the 2u minus, now plug in 0 for v, you get e to the 0, which is 1, so minus 1. I guess I don't need all those parentheses. I can just do e to the 2u minus 1 du. And now integrate that. We have 1/2 times antiderivative of this is 1/2 e to the 2u. Antiderivative of 1 is u. Evaluating that from 0 to 3. And we should be there. Let's see. Plug in 3 first. So I have 1/2. Plug in 3 here, get e to the 6th, half of e to the 6th. Minus, plug in 3 here, 3. That's what I get when I plug in 3. Minus, now let's plug in 0. So 0 in here, I have a 1/2 in front. So 0 in here, e to the 0 is 1, so I get 1/2. And then 0 in here, you get minus 0, so that's it. And so at the end of it all, I get distribute through, I get 1/4 e to the 6th, distribute here, minus 3/2, and then minus 1/4 when you multiply those two together. So you get 1/4 e to the 6th. Let's see, 6, 7, minus 7/4. I guess you could pull a 4th out of there if you wanted to. It's up to you. Yeah, you can pull a fourth out, that's fine, but I'm just gonna leave it. All right, that will do it for 12.8.